Okay, section 8-4, worked on a system by an external force. So we're no longer going to be as isolated, at least not in physics land. So we can extend our understanding of work to, instead of just being a work done by a particular force, we can have work done on a system. So work can be energy transferred to or from a system by means of an external force acting on that system as a whole. So if you have a system of more than one particle, work can change both the kinetic energy and the potential energy or other forms of energy in the system. So for instance, in this figure down here, right, if you lift a bowling ball where the system is the ball and the earth, you are providing an external force to lift the bowling ball, and you're transferring energy to both the kinetic energy and the potential energy. So in terms of math speak, the work done in lifting the bowling ball is equal to a change in kinetic energy plus a change in potential energy. Or in other words, the work done by this external force is equal to the change in mechanical energy. This is still considering a frictionless system, but at this point, we can add in friction too. So if you have a system with friction, we describe that as our thermal energy, so delta E sub TH, with the TH is for thermal. And the way we calculate this thermal energy increase is the force of kinetic friction, F sub K, which we know we calculate with the coefficient of kinetic friction times the normal force, and then times D, the displacement. So this is the increase in thermal energy by sliding, and that modifies our last equation to just add on an extra term, right? That some of the work that you might be putting into the system, like to push a block, might be lost to thermal energy, and it might not all go into increasing the mechanical energy. And so where this thermal energy comes from is the forming and breaking of the welds between the sliding surfaces, which is pretty cool. So here's a figure where there's an applied force that supplies energy to move the crate forward, but not all of that forward force goes into moving the crate and changing its kinetic energy or its velocity, because the frictional force transfers some of that external work into thermal energy. Okay, so here's another checkpoint. So once again, I encourage you to be ready to pause this. I'll read it once first. In 3 trials, a block is pushed by a horizontal applied force across a floor that is not frictionless, as in the figure. The magnitudes F of the applied force and the results of the pushing on the block speed are given in the table. In all 3 trials, the block is pushed through the same distance d. Rank the 3 trials according to the change in thermal energy of the block and floor that occur in that distance d, greatest first. Okay, so go ahead and pause so that you can think about this, and please write down the answer. Okay, hopefully you've paused. So now we can check what it is. So the answer is D. All the trials result in equal thermal energy change. Why is this? Well, the key is that our value of the force of friction is the same. Since the coefficient of kinetic friction only has one value, it doesn't matter how fast that crate is moving. Just the fact that it moved the same distance d, and the force of friction had to be the same for that same distance. Now, these 3 blocks may have taken a different amount of time to get there, right? The one that's going increasing in speed is going to have get to the point D sooner than the one that's slowing down, but they all went that same distance. So with that thermal energy, since it's the force times the distance, the force of friction times distance, it is indeed the same for all of them. So nice that we can look at the end result there, get a sense of the big picture. And now we have a way to describe friction's effect on our conservation of mechanical energy as well. So until next time, have fun and see you soon.